Hello friends, welcome in this video session of heat pumps of refrigeration and air conditioning subject. My name is Mr. S. V. Kumbhar, Assistant Professor, Sharad Institute of Technology, College of Engineering, Yedrao, Ichalkaranji. So this is the outline of today's video lecture. We will start from definition, operating principle, types, performance evaluation, application and issues related with heat pump. So first we will start with definition of heat pump. So a heat pump is a device that produces heat energy from a source of heat to a destination called as heat sink. In earlier lectures of basic thermodynamics subject, we have studied heat source and heat sink. Heat source is a source which is having ample amount of heat. Even if we reject few amount of heat, its temperature will not be affected. Similarly, heat sink is that sink where if we reject some amount of heat, its temperature will not be affected. So in heat pump, in this figure, heat is continuously extracted from low temperature body. That heat is supplied to high temperature body provided that the temperature of high temperature body is kept at utmost high temperature. For that purpose, we have to supply work to heat pump. So heat pumps are designed to move thermal energy opposite to the direction of spontaneous heat flow by absorbing heat from a cold space and releasing it to a warmer one. So heat pump provides heat. That heat is supplied to high temperature body and the temperature of high body is maintained above atmospheric temperature. Heat pump provides cooling. In low temperature body, the cooling effect is produced because of continuously extraction of heat energy from low temperature body. So the temperature of low temperature body is maintained below than that of atmospheric temperature. Heat pump also operates on electricity. Electrical energy has to be supplied to heat pump so as to operate. It's a cost effective because simultaneously at high temperature body the temperature is maintained above atmospheric temperature, and in case of low temperature body the temperature is maintained below atmospheric temperature. The examples are refrigerator and air conditioning. These are the examples of heat pump. So the term heat pump in broader sense applies to numerous heating, ventilation and air conditioning devices employed to heat or cool spaces. Generally, air at -18 degrees centigrade contains about 80% of heat that it contains at 21 degrees centigrade. So this is the ability of ground and air outside building to retain a considerable amount of heat is very well exploited by a heat pump, which can be used to cool and condition air inside building, as in air conditioner as well as heat buildings on cold days. So coming to operating principle, as we have already seen, in a heat pump, heat is continuously extracted from low temperature body. That heat is supplied to high temperature body provided that the temperature of hot body is maintained above atmospheric temperature. So a heat pump can absorb heat from a cold space and release it to warm space. But heat energy is not conserved in this process, which require some external high grade energy, that is electricity with less entropy for the movement of heat in a direction opposite to the natural course of flow. So in the heat transfer we have already studied, spontaneously heat will flow from high temperature body to low temperature body because of temperature difference. But here heat will flow from low temperature body to high temperature body. For that purpose we have to use heat pump. The working of heat pump can be represented mathematically by a model that is known as heat pump or refrigeration cycle. So in this light, a heat pump can be thought as a heat engine which is operating in reverse manner. So operating principle of heat pump. So in the figure, different components are shown. Here first heat pump is shown, heating cycle and drying cycle are shown. So in heat pump, two major components, that is evaporator, condenser, those are shown with the help of different colors. So blue colored is evaporator and red color is condenser. So generally it works on refrigeration cycle. In compressor, there is third component, compressor. Here it is shown, compressor. In compressor, vapors of refrigerants are compressed, due to which high pressure, high temperature vapors of refrigerants are shown. Here the pressure and temperature is shown. It's a 17 bar and 36 degrees centigrade. This high pressure, high temperature vapors of refrigerant flows towards condenser, where it is condensed with the help of heating cycle. We can use either air or any cooling medium in this condenser, due to which condensation of refrigerant takes place. It is converted into high pressure, low temperature liquid refrigerant. This high pressure, low temperature liquid refrigerant, when passes through expansion wall, where its pressure drops down, that is to 5.5 bar, and temperature is reduced to -4 degrees centigrade. This low pressure, low temperature liquid refrigerant finally flows through evaporator, where cooling effect is achieved in the heat pump. That heat can be used with the help of brine cycle, and in this way heat pump works. As I said, generally it works on vapor compression refrigeration system. So there are four important components of vapor compression refrigeration system: compressor, then condenser, expansion wall, evaporator. So this is high pressure side and this is low pressure side, right? So first component is shown as fan. A fan passes ambient air over the evaporator. The refrigerant boils and evaporates at low temperature. So cooling effect is achieved. After that, vapors of refrigerant are compressed in the compressor, due to which again it increases pressure and temperature of vapor. This high pressure, high temperature vapors flows through condenser. At the same time, we can use either air or water as a cooling medium. Other than this, we can also use cooling medium, but these are naturally available and freely available. It can be available easily. That's why we use water or air as a cooling medium, due to which its temperature drops down. High pressure, low temperature liquid refrigerant finally flows through expansion wall, where its pressure drops down considerably, and here again cooling effect is achieved. This is vapor compression refrigeration cycle, which is used in heat pump. So the various process of vapor absorption cycle are very similar, but only one method of compression of refrigerant is different. In vapor absorption system, ammonia is used as refrigerant, which has very high affinity to dissolve in water. So remember, ammonia is easily soluble in water, that's why it is used widely in vapor absorption refrigeration system. So absorption of refrigerant. In absorption system, there is no traditional compressor. Compressor is replaced by absorber and generator. We have already studied. So instead there is absorber. The absorber consists of water, that is called as absorbent, in which the refrigerant ammonia dissolves. This mixture of water and ammonia is then pumped and heated with the help of waste heat energy, and due to which there is increase in temperature and pressure of ammonia. So again, this is vapor compression cycle, which is working on electricity that we used in domestic refrigerator as well as chilling system. Different types of heat pump. Heat pumps are classified on the basis system installed within heat pump unit itself, motive or generating power unit, temperature of operation. These are the different types of heat pump. So first one, system installed within. Air source heat pump system. So in this heat pump, heat is extracted from ambient air, which is drawn across heat exchanger. Heat source temperature will be dependent on prevailing ambient temperature and varies through the year depending on geographic area, that is typically average 6 to 8 degrees centigrade. Ground source heat pump system. In ground source heat pump system, a closed pipe loop of water and antifreeze solution is buried in the ground, either vertically through boreholes or horizontally in trenches, that is coiled or straight in length, and the heat pump used to extract the heat. Supply temperature will be around 0 to 5 degrees centigrade in order to extract heat from source at 10 degrees centigrade, which is most common form of ground source, where water is passed through the source inside a tube heat exchanger. Water source heat pump system. There are two types of water source heat pump system: closed loop and open loop. In closed loop, work loop of water and antifreeze solution is sunk into a river, lake or sea. Here, supply temperature will be approximately 5% less than source at about 0 degree centigrade. Where in open loop system, water is actually extracted from a water aquifer and passed through the heat pump, sometimes using a protective passive water to water heat exchanger. Source temperature will be close to ground temperature unless a heat exchanger is used, hence at about 10 degrees centigrade. Other types: water loop heat pump system, exhaust air system. So based simply its source and delivery medium, these are the different types of heat pump: air to water, air to air, water to water, water to air, depending upon heat transfer medium. So heat pumps are also sometimes designed by the fuel source used to drive the process within, which is almost electricity, that is greater than 95%, less commonly natural gas and much lessly LPG. So this is the figure of two-way heat pump. So two-way heat pumps work in either of thermal direction to provide cooling or heating to an internal space. So in first figure, cooling effect is shown. In the second figure, here heating effect is shown. They employ a reversible wall to reverse the flow of refrigerant from compressor through condenser and evaporation. So one check wall is used. So high pressure, high temperature vapors of refrigerant, if it directly passes, then generally heating effect is achieved, and if through evaporator low pressure, low temperature refrigerant flows to indoor coil, then generally cooling effect is achieved. Means here indoor cooling effect is achieved and outdoor here from outdoor coil. So this is all about two-way heat pump. So flow temperature for heat pumps, generally hot water in the condenser, that is air to water or water units. Another sub description is given here, that is low temperature 35 degrees centigrade, medium temperature 45 degrees centigrade, high temperature 55 degrees centigrade, and very high temperature 65 degrees centigrade. So coefficient of performance. So in earlier lecture we have studied efficiency. In very similar manner, coefficient of performance, that is COP, is a measure of amount of power input to system compared to amount of power output by the system, and COP is given by power output upon power input. Generally that power output is refrigerating effect, power input is electricity which is supplied to heat pump. The COP therefore is a measure of efficiency. The higher the number, more efficient is the system is. So an example is shown here. Consider a simple electrical heater. So all of the electricity that is input to unit is converted into heat, that is electrical energy is converted into equivalent amount of heat. There is no waste of heat, and power output in terms of heat equal to power input in terms of electricity. So COP is 1. The COP can be used to describe any system not just heating and cooling. The maximum theoretical COP of an air conditioning system is expressed by Carnot's theorem. That is, maximum COP is equal to Tc upon Th minus Tc, where Th is the highest temperature, Tc is the lowest temperature. Performance evaluation of heat pump. Performance evaluation means when heat pump is more efficient when the room temperature is closer to outside temperature and will use more power when there is a larger difference in this temperature. Generally, COP value for air conditioning and heat pump are in the range of 2 to 4 or about 10th of theoretical maximum efficiency or COP. Now, applications of heat pump. As we have studied, heat pump is generally used for heating purpose and cooling purpose. So, district heating, that is the most important application of heat pump. District heating is a district heating system in the Drammen, Norway. The heat pump was manufactured by Star Refrigeration in 2011 with 3 systems giving a combined capacity of 14 megawatt to central Drammen, providing 85% hot water needed for the city. The refrigerant used were ammonia, source seawater, that is 8 to 9 degree from depth of 18 meter, district water heated around 65 degree to 90 degree for use in building heating and hot system. The average COP was 3. Second important application of heat pump is drying. So, these heat pumps gives the possibility of waste heat recovery. With the heat pump, the heat which is extracted from exhaust air is upgraded to higher temperature level, and when air is heated, that hot air can be used for drying application. Washing. This is one more application of heat pump. The washing installation is often equipped with air discharge fan to prevent the installation from vapor flowing out through the inlet and outlet opening and other opening in washing machine. So, one typical example of washing machine is shown here. So, hot water which is produced with the help of heat pump, which can be directly circulated to water tank, and this hot water is used for washing purpose. The air discharge will blow humid hot air to ambient surrounding and will maintain an under pressure inside the washing machine. The discharge air contains a large amount of energy with heat pump. Next important application is pasteurization in dairy. In most pasteurization process, heat exchange between cold and hot product flow already implemented. In addition to this, extra heating and cooling are needed for pasteurization. For that purpose, heat pump is used. This heat pump might be the ideal solution to extract heat, the product that is needed to be cooled or heated, and supply this heat to high temperature to product that needs to reach pasteurization. Next application, cogeneration. In designing a cogeneration, heat pumps readily complement with many renewable energy technologies to produce desired heat and power at reduced basic fuel input. Therefore, integrating heat pump with clean technology becomes a potent tool in combining carbon emission. This is the direction energy engineering should be moving with all deliberate speed. This heat pump can be easily collaborated with clean sources, that is wind energy, that is PV cell, desalination of seawater. Desalination is the process of converting seawater to fresh drinkable water. Desalination plant based on mechanical vapor compression refrigeration system are inherently the most thermodynamically efficient. Thermal desalination requires lot of energy. One hybrid technology that can be potentially lower energy consumption is solar assisted heat pump, which operates at low temperature and utilizes solar energy, ambient energy and waste heat so that water can be converted, that is salt water can be converted to fresh water which is used for drinking purpose. But there are some issues related with heat pump. So first issue is, as with any heat engine till date, even heat pumps share the major flow of constrained performance parameters due to thermodynamic efficiency limits. So efficiency is not more than 40-50%. Heat pumps are only highly efficient when they generate heat at a low temperature differential, ideally around below 32 degrees centigrade. Third issue, both indoor and outdoor heat pumps unit contain moving mechanical component which produces noise. Noise is the biggest disadvantage which can be taken as research related work in case of heat pump. So these are all the contents we have covered. Thank you very much.